Alright, we have another forced convection over a flat plate question. So we have, consider a laminar flow of a fluid over a flat plate at a constant temperature. And so the free stream velocity is doubled. So V2 equals 2V1. Determine the change in drag force and the rate of heat transfer. So the change in the rate of heat transfer, and assume the flow to remain laminar. Cool. So we aren't given any numbers other than changes. So all of the numbers will be changes, and there will be some numbers from just the analytical solutions. So the first thing we look at is the change in drag force. That's part A. So what is drag force? We know the formula for drag force is CFAS. So the coefficient, then times the density times velocity squared by 2. So that is what the drag force is. And CF is analytically, for laminar, about 1.33 over the square root of Reynolds number. Cool. So then we can substitute that into this equation with CF. So we have FD is actually 1.33 times the surface area divided by the square root of Reynolds number times rho v squared by 2. All right. We also know what Reynolds number is. Reynolds number is VL over the kinematic viscosity nu. So I'm going to erase that Reynolds number and then multiply it by VL over curly V. There's something I notice here. We have this V squared on top and the square root of V on the bottom. So we can combine these. I'm just going to do a little bit of exponent review here. We have a x, for example, to the 0.5 on the bottom, and we have x squared, where in our case x is v, but we're just doing some exponent review. So this is going to be the same as when we divide exponents, we just subtract them. So x squared minus 0.5. So this is going to be x to the 1.5 or 3/2. So when we clean this up, this will be v to the 3/2. So let's go clean that up a little bit. We also notice there are some constants here, 1.33 and 2. So we say 1.33 over 2. That is about 0.664. So that's what these constants get sucked up by dividing them. And then we have v to the 3/2 from exponent rules. Then we have AS, surface area, times the density rho. Now I have to worry about the square root L and square root curly V. So we still leave this as L to the 0.5. And because this is on the bottom of the bottom, by fraction rules, we can bring that up. So now if we say that this is doubled, this velocity v is doubled, we say fd2 we substitute in 0.664 v times 2 to the 3 halves, and all of this is just the same. So I'm actually not going to worry about that because it will all end up canceling out. So the ratio of f's we have fd2 over fd. We have the 2 substituted in, and the v to the 3 halves substituted in. If I had kept these values, the 0.664s would have canceled out, and all of these would have canceled out because they're just 1. 0.664 divided by 0.664 is 1, and anything divided by itself is 1. So this divided by itself is 1, leaving this. Well, because of rules of exponents, we can actually break this up. This is being added. So we actually have 2 to the 3 halves times v to the 3 halves. So just like everything else, v to the 3 halves cancels, and we are left with 2 to the 3 halves is the ratio of fd2 to fd. Okay, so the next part says, and then we're going to do the same thing with the rate of heat transfer. So we're going to again work backwards from Q dot. The formula for that is HA TS minus T infinity H is also K over L times the Nusselt number. This is just the equation for the Nusselt number, but rearranged solving for H. And then, of course, keep AS times delta T. I'm just going to have this be delta T, so it's slightly faster to write. Then, of course, we have our equation for the Nusselt number. So we have K over L. The analytical solution for the Nusselt number is 0.664 times the Reynolds number to the 1/2 times Prandtl number to the 1/3. Then we say A delta T. Well, just like before, we can substitute in the Reynolds number. So we have 0.664 times Reynolds number to the 1/2 VL over curly V to the 0.5 times Prandtl number PR A S delta T times K over L. Cannot forget that. We could do a similar trick with these L's because we have a 0.5 and a 1. So 0.5 minus 1, or 1 over the square root of L, if we really wanted to. However, I'm not too concerned with cleaning it up, as Q dot 2 is 0.664 times. I'm going to leave this as 2v square root times L to the 0.5 over v to the 0.5. Prandtl number, surface area, delta T, KL. So now when we do Q dot 2 over Q dot 1, we've already have everything ready. So now we're left with everything canceling out. We have square root 2v over square root v, because v to the 0.5. The 664's cancels, the Prandtl numbers, the AS delta t k over L, all of that mess cancels out, and we're left with this. Similar to the exponent breakdown over here, the square roots are really just exponents, so we can actually just cancel out the square root of v, and if you're confused why, we can break this square root of 2v, square root 2 times square root v over square root v, square root v's cancel, and we are left with square root 2 is equal to the ratio of the rate of heat transfers. Boom.